The purpose of this exercise is for me to clarify really what reversible and irreversible cycle means for the system and for the surroundings. So this is a problem that I gave in midterm last year, and it starts out with a reversible cycle, and here it is. It's shown on the PV plane, and you can see that the legs are labeled 1, 2, 3, 4, so you go around the clock here, actually counterclockwise. Legs 1 and 3 are, 1 is an adiabatic expansion, 3 is an adiabatic compression, and 2 and 4 are isobaric processes. 2 is an isobaric expansion, and 4 is an isobaric compression. And I think the statement of the problem says that initially you have an ideal gas. And the first part of the problem states that the cycle is reversible. And the questions are, when I go over one cycle, what is delta S of the gas, delta S of the surroundings? And I ask you to sketch S versus V. So while we learn how to figure out how to put quizzes in the screencast, what I will ask you is to write here or on a piece of paper whether you think that delta S gas is larger, smaller or equal to 0. Delta S surroundings is larger, smaller or equal to 0. And then sketch S versus V. So pause the screencast, do that. And then the screencast will continue with me solving the problem for you. But this works best if you try it by yourselves first. Here's a solution to the first part of the problem. So first of all, delta S gas, when the gas goes through one cycle. Well, this one is simple. You just have to think that S is a state function. And so if the gas goes back to its initial state, then delta S must be equal to 0. It doesn't matter whether the cycle is reversible or irreversible. The gas goes back to its initial state. Its change in entropy is 0. Now for the surroundings, you have to think a little bit more. We don't necessarily know whether the surroundings go back to their initial state or not. We don't really have much of a statement about the surroundings. But remember that if the cycle is reversible, delta S gas plus delta S surroundings, this is equal to delta S universe, and this is equal to 0 because the cycle is reversible. So now we use the hypothesis of reversibility. Because delta S of the gas is 0, delta S of the surroundings has also be equal to 0. So now we are ready to sketch S versus V. Here it is. And I will sketch it in black for the system and in red for the surroundings. So let's start with the system. We have V1 here, V2 here. I don't know what the initial entropy is. I don't really care. I'm just going to sketch. It's a sketch, so it doesn't have to have numbers on the left axis. So the first process, process 1 from V1 to V2, is reversible and adiabatic. And because remember that ds is larger or equal to dq over t, and the equality holds if it's reversible. So ds equals dq reversible over t. If it's adiabatic, dq reversible is 0, and so ds is 0. So the first part for the system, no change in entropy. Going from V2 to V3, the gas is expanding at constant pressure, and we have a statement at the beginning that it's an ideal gas, and so we know that PV equals RT. The pressure is constant, so the volume is increasing. It also means the temperature is increasing. And you remember for an ideal gas, S goes like CV log T plus R log V, and so it has to increase as I expand the gas. Now when I go process 3, from V3 back to V4, we have again adiabatic and reversible. It's a compression, but it doesn't really matter because S has to be constant. And then when we go back to V1, This is simple. I don't even have to think about it. It has to go back to the initial entropy because delta S is 0. So here are our parts of the process. Now, what about the surroundings? Well, the process is reversible, so everything that the system does, the surroundings must mimic and cancel out so that delta S of the universe is equal to 0. So the first part from V1 to V2, no heat is exchanged. S of surrounding stays constant. When the gas expands from V2 to V3, it must be absorbing heat, so it must be absorbing it from the surroundings. And so ds surroundings is equal to del Q integral of del Q over T, and del Q is negative, and the delta S of the universe of the process has to be equal to 0 because it's a reversible process. And so the surroundings, I'm not drawing it very well, but it has to cancel out exactly what the system does. And then the same reasoning applies everywhere. And here is what happens to the surroundings. I'm sorry about the drawing here. This is flat, and then it goes like this. Sorry about that. 3 and 4. Here's the second part of the problem where we have an irreversible cycle. In fact, the only part of the cycle that's irreversible is leg 1. And what we do in leg 1 is we let the system go through an irreversible expansion. It's still adiabatic, but it's irreversible. So the way to picture it is we start here at a volume V1, and I have my little weights, and I put some blocks here at the volume V2. I remove one weight, the piston goes up adiabatically and irreversibly or spontaneously until it slams against the two blocks at volume V2. So it expanded this way. After this, the cycle remains reversible. So leg 1 prime, the pressure drops to the pressure that the gas had originally at the end of the reversible adiabatic expansion. Remember, the reversible adiabatic expansion went like this. And then the rest of the process is reversible. Here's a list of questions. Why is the pressure at the end of leg 1, at the end of the only irreversible leg, higher than what we had in the reversible case where the pressure was here? So why is this pressure here, P, let me call it 2 prime, larger than P2? What is the physical process that occurs here? What is delta S gas? Is it positive, negative, or equal to 0? Delta S surroundings, positive, negative, or equal to 0. Sketch S versus V. And the last question is, what would the answers be if the gas were not ideal? So again, I suggest that you pause the screencast, try to answer the questions, and look at the solution only after you've actually tried solving the problem by yourself. First question, why is the pressure at the end of leg 1 here, so P2 prime, why is it higher than P2? Well, we've seen this in class because when you do the reversible work, del W is equal to minus P external dV. And in the reversible case, this is equal to minus P dV. But in the irreversible case, minus dW irreversible, it's still equal to minus P external dV, but in the irreversible case, P external is smaller than P internal, or P of the gas, and so the irreversible work in absolute value is less than the reversible work. In this case, the work is negative, and so if the gas has done less work, it will have cooled down less, so it will have lost less energy, so delta U is smaller. So this means that delta T is smaller. And so if the final volume is the same, it means that T, let me call it 2 prime, the temperature at this point is larger than the temperature at this point here. And so we conclude that P2 prime has to be larger than P2. What is the physical process in leg 1 prime? Well, in leg 1 prime, you can see that the pressure is dropping. at constant volume, because PV equals RT. If the pressure is dropping, it means that the temperature is dropping, so it means that heat is being transferred to the surroundings. So the process that's occurring in leg 1 prime is the piston is not moving and heat is being transferred to the surroundings. Okay, what is delta S gas and delta S surroundings? The gas goes through a cycle. S is a state function. So remember, it doesn't really matter whether the cycle is reversible or not. Delta S of the gas will be equal to 0. Now, the cycle is irreversible, and so delta S of the universe, that has to be positive. And so you conclude that delta S surroundings has to be positive as well. So here is the key to reversibility. Now you can think the system went back to its original state, so it's reversible. But what is not reversible is the universe. And so you always have to remember, reversibility does not refer to the system, it refers to the universe. So sure, the system went back to its point 1, initial point here, but the surroundings did not. When the system has gone through one cycle, the surroundings is not exactly the same as what it was before it started. So this is what irreversibility means. It's irreversibility for the universe. Don't get tricked by that. You can design cycles that are irreversible, but where the system actually goes back to its initial point. This is a classical case. And now for the entropy versus volume. So let's look here at the system on the left. This is the initial entropy of the system when it's sitting right here. And I'm going to put a horizontal dashed line. So the first process is an irreversible adiabatic expansion. Now you know that ds in that case has to be larger than del q over t. Because del q is equal to 0, ds has to be positive. So when I go from v1 to v2 in process 1, the entropy has to increase. Now process 1 prime, the system is essentially, the gas is giving heat to the surroundings to cool down and drop its pressure, and it's done at constant volume. And what we know is that by the end of this process, the system is exactly where it was when it expanded adiabatically. And so if I call this S initial and this S2, S2 minus S initial has to be equal to 0, because I can get to point 2 with a reversible adiabatic expansion where delta S is equal to 0. So I know that the entropy has to decrease here at constant volume back to its initial value. The rest of the process stays the same as before because it's reversible, just the same as before. So during the expansion, the entropy increases, then during the adiabatic compression, it stays constant, and then it has to come back to the initial point here. So it has to do something like that. So this process, this leg here is 1, this leg here is 1 prime, this leg here is 2, 3, 4. We go back, delta S of the gas is equal to 0 at the end of the cycle. Now let's look at the surroundings. So I'm going to put the same dashed line here. When I go from V1 to V2 with the adiabatic expansion, there is no heat exchange between the surroundings and the system. And so this means that the entropy of the surroundings has to stay constant. So this is leg 1. Now leg 1 prime, the surroundings is giving heat back, the system is giving heat back to the surroundings at constant volume. And so this means that the entropy of the surroundings has to increase. And it has to increase by this amount here. The rest of the cycle stays the same. So during the expansion to V3, the surroundings is providing heat, and so the entropy of the surroundings has to decrease. From V3 to V4, the entropy has to be constant, because, so this is leg 1 prime, this here is leg 2, this here is leg 3, and then leg 4 has to be compression, so the entropy of the surroundings is now increasing because heat is being dumped from the gas to the surroundings, and we end up at this point, we end up offset exactly by the amount that was given back to the gas after its adiabatic irreversible expansion, because that was the extra entropy that the system had, that it had to give up to the surroundings to go back to the same initial entropy state it had when it started. And so if this is S final of the surroundings, here you can see that delta S of the surroundings is positive as it should be. It ends up at a higher entropy than what it started, and it's all due to this leg here. So this is leg 4. Would the answers be different if it was not an ideal gas? Well, the shapes of these curves may be different, but in the end, I've never really used the fact that we're dealing with an ideal gas here. So the shape of the curves would be different, but the answers, generally speaking, would not be different. What is the point of this exercise, and what is the moral of the story? The moral of the story is when you see a cycle, the system that goes through the cycle, of course, always goes back to its initial point. That's a definition of a cycle. Whether it does it reversibly or irreversibly, if the system goes to a cycle, it means it comes back to its initial point. And so you may think that this means that it's reversible. For the system, you always have delta S of the system is equal to 0 in a cycle. What makes it reversible or irreversible is delta S of the universe. Because delta S of the system is 0, what makes it reversible or irreversible is delta S of the surroundings. So never forget that. It's the surroundings that don't go back to their initial state in an irreversible cycle. The system can very well go back to its initial state, but for the cycle to be truly reversible, the whole universe has to go back to its initial state. So what you have to pay attention to in a cycle, whether it's reversible or irreversible, is the surroundings. It's the surroundings that don't go back to their initial state.